Thumbs up, thumbs down. Sweet. All right. So hello everybody. Thank you for coming. This room is a lot more packed than I was expecting, so that's great. So I'll introduce myself. My name is Sam Culver. I'm a WPILib developer. I've been developing for WPILib since 2012, I would say, when I started as an intern in high school. And I've stuck around ever since. This talk is Commands v3, the next commands framework. This is not replacing the current commands framework. You'll continue to be able to use the existing commands framework for at least the next few years. We expect teams to gradually migrate over to using v3. And when a majority of teams are using v3 and are comfortable with it, then we'll look at phasing out v2, so we don't have to manage two separate commands libraries. That's a lot of commands already. So, without further ado, I'm going to start with a couple of definitions, just so everyone's starting with a solid framework here. So, commands. At a basic level, commands are basically functions that you can store and then run later. That's basically all it is. They tend to control physical hardware. That's usually what they do. You can use commands for doing other things. A common thing is like changing vision pipelines, for example, on a limelight. You could have commands that change the limelight's vision pipeline if you don't want two commands running at the same time. So that's something that you would use commands for that isn't directly controlling physical hardware. And a key part of this is that they provide collaborative concurrency. So if you want to control multiple mechanisms at once, that's when you want to start using commands, because that makes it easy to do that kind of collaborative multitasking without having to step into threads and all of the headaches that come with multi-threading. And of course, they're managed by a scheduler. You've all probably seen command scheduler.getInstance.run in your robot periodic loops. That's the command scheduler managing all the commands, managing your triggers, all the events, and making sure that everything is running as they should. And just, you've seen this code already, right? You create a trigger, you create a new command, you bind that command to the trigger, and then when the trigger fires at some later point in the future, your command will execute. So this is, you create the command, maybe at startup, maybe at some other point at runtime, and then eventually that gets scheduled due to some of that happening with your triggers were managed. So let's talk about coroutines. So coroutines are suspendable functions. So most functions that you're working with in Java right now, or actually every function that you're working in Java right now, is a blocking function. So when you call that function, it will run until it finishes, and then whatever called that function will then get to go on and do whatever the next step is. But it can't do anything in the middle while your function is running. But coroutines are suspendable. You can yield inside the coroutine to say, I've reached a stopping point, or a point where I'm comfortable pausing to let some other code execute. You can probably see where this is going with commands. And of course, coroutines are managed by a scheduler, because the scheduler has to mount the coroutine, it has to let it run, it has to wait till that coroutine finishes or suspends itself, and then the scheduler can continue to go on to do the next thing. Does this seem familiar to anyone? So here's a nice example that I found. On the left, this is basically showing what a blocking function does. You have your main code that is executing. It then wants to call a function. It has to let that function run all the way until it finishes, and then that function exits, and then your main code continues to go on and do something else. With coroutines, they can pause at any point inside of that coroutine function. So if you've hit a good stopping point, you can pause your coroutine function, say, I'm done for now, yield, go back to the scheduler, and then the scheduler can go on to the next thing. And then if your coroutine wants to run again later, the scheduler will pick it up, mount it, start running it until it hits its next yield point saying I'm done now. Or it just naturally exits. And when it exits, it's removed from the scheduler and then it's all cleaned up. So with that framework in place, let's talk about what the goals of v3 are. Number one is smoothing the on-ramp. This isn't just smoothing the on-ramp from the current v2 commands framework. This is also smoothing the on-ramp for people who have never used commands before. So you should be able to write normal code, basic stuff, and then you should be able to take that code that you've learned how to write and put that into the command framework. That's like the key thing that I'm focusing on with v3. The next thing is that we want detailed telemetry. So who here has had trouble debugging commands before and had, this is a big show. Maybe a third to a half of people here have a hand up. So command debugging is a huge pain in the butt right now because the command scheduler only knows the topmost commands that are executing. It doesn't know anything else. So if you're having complicated command sequence going, it only knows the sequence that's running. It doesn't know where in that sequence that command is. It doesn't know what the heck is going on, other than, oh, you're running your autonomous right now. Like, okay, well, what else is that auto doing? You have no idea. So then you have to go put in print statements or whatever else, split up your commands to try to figure out what's going on. And the last thing is a sensible ownership model. This is a little bit more advanced. So ownership, this is saying your command has ownership of a particular mechanism or a group of mechanisms while it's running. We want that to make sense, to be obvious, especially when you start doing more complicated kind of compositions. That's also another pain point with the current commands framework that I want to clean up. So let's start with that first point, transitioning from non-command code to command code. So who here is writing code like this? This is like baby's first autonomous, right? This is, you want to drive a certain distance, you have an encoder, you have a motor, you wait until your encoder has measured some distance that's been traveled, and then you stop most, right? Like, you've all probably written this, basic, first day program with a robot kind of code. This is the V3 command version. That's it. So that's like the thing that commands V3 lets you do. That's what coroutines lets you do. The only change here to your logic is that coroutine.yield function. This is saying that at the end of every loop, after you check your encoder distance and you still haven't hit your target, I want to pause my command right now because I've hit a stopping point. I've done my work. I want to yield. I want to pause here so I can let some other command run. So you need that coroutine.yield. There's actually a compiler check right now in WPILib that will check your while loops. If you don't have a coroutine.yield in your while loops, in your commands, you'll get compiler error. Because we don't want you to be writing infinite while loops, forgetting to yield, and then your commands are just running infinitely and you're stuck doing one thing until that fixes. Like, that's a runaway condition. We don't want to do that. There's compiler checks in place that do that. There's also a few other compiler checks and runtime checks that help enforce safety so that you try to remove footnotes, basically. So the last thing you want to do is that run function that returns a command, we want to actually return that from this function that gives you a command. And the last thing is that named drive distance at the end. That's saying that this command has a name. Every command in V3 must have a name now. That's hooking into telemetry. So that when you're trying to see what your commands are doing in your scheduler, you can guarantee that every command has a name. I can't guarantee that it has a sensible name. It's up to you guys to give it names. But you at least have to give a name so that you can see that in telemetry when you're trying to debug your code. So you can also compose commands. You can do that right now with sequential groups or parallel groups. But going back to that basic non-command code, right, the next step after driving in a line is driving to square, or doing a turn, doing more, doing multiple things in a sequence. So pretty basic, you have a for loop, 4 times, you drive straight, you turn 90 degrees, you drive straight, you turn 90 degrees, and so on. In V3, this is how you do that with a command. So this is introducing coroutine.await. This is saying, basically treating that drive distance that used to be just a normal function call that was blocking. Drive distance is now a command, turn 90, I assume that's also a command. Coroutine.await is saying, treat this command like a blocking function call. So when you call coroutine.await, that will schedule that new command. It'll wait for that command to run until its natural exit point, and then it'll, the coroutine.await will return, and then you can go to the next step. So here we're awaiting that drive distance. So it'll schedule that drive distance command to drive however far you're telling it to go, and then wait for that command to finish. And then once it hits its end, when it's exited, when your coders have said, okay, I've driven that distance you told me to drive, that first coroutine.await will stop, and then go to the next line. That next coroutine.await for that turn 90 degrees, and that'll be able to you can probably figure out what that turn 90 degrees command does. I don't think I need to go into detail there. And then again, the last step to this is say, you need to return that, and then give it a name. So again, this is a command sequence. You could do this, right now, right, with a sequential group. You just made, drive distance and then turn, and drive distance and then turn. You do that 8 times. You have 8 commands in sequence. You can do that right now in V2. You can also do a similar thing in V3. I'll touch briefly on that later on. So there's a bunch of things that coroutines let you do. This is all going to be the API documentation. You don't need to know this like right now. But we saw the yielding, so that's basically saying, in my command, I reach a pausing point. The scheduler can stop this command running right now and then go on to the next thing. So if you're running multiple commands at once, That's saying, okay, your first command in your scheduler is running, it yields, scheduler pauses that, puts that on the back burner, picks up the next command in the queue, runs that until it yields, and et cetera, et cetera, et cetera. You can park, that's basically just yielding an infinite loop. There's compiler checks that you can't have code execute after a park call because that basically, that's unreachable code. So that's code that we don't want you to assume is going to run. So there's a compiler check for that. Forking, this is saying I want to run a command in the background. So that's like await that we just saw, except that it doesn't wait at the end. It'll schedule it, it'll run in the background, and then your main command that forked it can go on to do something else while the other thing is still happening in the background. Awaiting, like we saw, will fork it and then wait for that to finish, and then that await call will only return itself after the command that's waiting to finish is actually finished. Await all, that operates on a bunch of commands all at once. It waits for them all to finish, and when they're all done, it'll unblock, and then your command will be able to do something else. Await any, same thing. This is like a race command, if you're familiar with that in V2. It'll wait for any of those commands in that list to finish, and then cancel whatever is still running when the first one wins. Wait for, waits for a time period. I'll get to you in a second. I just want to finish this, okay? So wait for, that's like a wait command right now. So you give it a certain amount of time you want to wait, and then it'll just yield in a loop until that time period is elapsed. Wait until some condition is reached, pretty basic. And then for anything that's not listed here, you can get access to the underlying scheduler object. So if you want to do something more advanced that coroutines don't provide for you naturally, you can pretty easily hook into the scheduler to get access to that. So one question over here.
Can we join commands that before?
Yeah, that's what await does. So awaiting, so because the scheduler's a little bit smarter now, if you have a command that's running, like if that object is currently running in the scheduler, and then if you try to reschedule it, it will just return immediately because it's already running. But it'll still wait at the end. So that's basically, so you can fork, and then you can wait for that command to finish at some later point.
It's the same then.
Yeah. So like if you want to fork something to run and they want to do something meanwhile and then wait for that first thing to finish, you would fork it first, do whatever you want to do after forking, and then you wait. The key thing is that you have to wait for that same command object. So you need to keep a handle to that object because you fork it and then you have to wait for that single thing later. If you fork a different instance than the one that you're waiting for, the scheduler won't know that, right? Because it's easier to do two different things. So that would act as if you're scheduling a new command. So that would interrupt the one that you had forked. Does that one make sense? Cool. So let's do a little bit of the formality here. So when you declare a command, the command must have requirements. That can be empty. It can be an empty set or a set of one or more items. It needs to have a body. That's the function that you want to execute. That gets passed to the coroutine. The coroutine will then run that in the background. And it has to have a name. And that name is really for telemetry so that you can debug your programs. There's a couple of optional things. You can add a priority level to it. So if you want a high priority command, that can interrupt a lower priority command. That's kind of similar to the interrupt behavior that we have in V2 right now, except the interrupt behavior in V2, you have two states. You can either have your command ignore any incoming command and be uninterruptible, or you can have a command that will always be interruptible, which is the default. With V3, you can have a more fine-grained priority levels. So you can have a really high level priority, really high priority command, medium priority command, no priority command, and then they'll all interrupt each other or not interrupt each other based on that priority level. And then also you can have an on-cancel callback. This is similar to the interrupted callback that we have right now. That will only execute when that command gets canceled. Or an interrupt is also cancellation, so that will also happen when a command is interrupted. Usually you'll sometimes see this, which is why it's an optional callback. I can talk about the technical reasons why this has to be done separately after, if people want to talk about that. But not to go on a tangent here because I'm 13 minutes in and there's still a lot to talk about. The last thing is that these are created using builder objects. So that's necessary so that we can guarantee that you have every required piece of your commands in place when you create the commands. And I see one hand up over here.
What's the behavior with equal priorities?
The question is, what's the behavior with equal priorities? The behavior there is what it currently is. So if you have one command running to say priority level 10, and you have a new command coming in that shares a requirement also with priority 10, that new incoming command will interrupt that existing one. And so here, right, this is the stage builders. So your first step is to say, I have a command, I want to require some number of things. That returns a builder stage, and then that builder stage provides you methods that you can call to go on to the next stage of creating your commands. There's some helpers for this. You don't have to go through all of this rigmarole every time you want to create a command. But this is basically what you have to start with. This is the 3 key parts. You say what you require, then you say what your function body is, and then you say what the name of the thing is. Yes, question?
What would the parallel deadline group?
What would a parallel deadline group look like in V3? That would be, so a deadline group is saying you have one command that you want to finish, and then you have a bunch of other commands that you don't care about, and those can run in the background, and then when your deadline finishes, you cancel the whole thing, right? So you can do that with, and this is something I don't have time to talk about, it's not included in the slide deck, but you can do that with V3 composition builders right now. You can also do that manually. That's looking like you fork a bunch of commands you don't care about, and then you await one that you do care about. And then you cancel all the ones that you have worked for. So our next step, this is mechanisms. This is similar to the subsystems that we have in V2 right now. They're basically one-to-one. Mechanism is just a little bit more specific for what we intend these to be used for controlling physical mechanisms on robots. It's a little bit more descriptive of the name, which is why it's a name change. There's a lot of debate over what these could be called, but mechanism is what we finally settled on. These provide factories for commands to create commands that automatically require that mechanism. Again, this is very similar to what V2 already has. You have run, which is what we saw earlier in the talk here, that accepts, or you pass that a lambda function, which accepts a coroutine parameter, and then you have your function body that does whatever you want with it, has your loops, has your if statements, whatever. There's also run repeatedly, which is a helper, so if you just want to do one thing over and over and over again, that just accepts a runnable, so you don't have access to a coroutine there, but it just lets you specify a loop body without having all the other cruft and boilerplate around it. And then there's also idle and idle for if you just want a command that requires a subsystem that doesn't actually do anything with it. And I just caught myself calling it subsystem, so still a bit of a new name. So you just have these helpers here. So you have your drive class, implements a mechanism, you instantiate it like normal, and then you can use that to create commands off of that drive mechanism. Yes, question?
You mentioned it's now supposed to be more about physical hardware. So like, if you have a lot of times you have a vision subsystem,
Yep.
Would you still use a mechanism for that, or would you use?
You would use a mechanism for that if you want to be able to control that vision subsystem to tell it to do something else. So if you want to switch between, say, like object detection versus vehicle type detection, you could represent that as a mechanism. Similar to that, like LED strips that aren't physical mechanisms but are still controllable. The key part is that a mechanism is something that is controllable. And you don't want that controllable thing to be doing 2 things at once and have conflicting commands issued to it. And that's the whole requirements thing. One more question over here.
If I could replace run once.
Yeah, so the question is, am I replacing run once and run with these ones run repeatedly? The answer is yes. And I thought I saw a hand up over here.
Does idle just override any command?
Idle has the absolute minimum priority by default. You can override that function. Like everything's overrideable here. So if you want your idle command to say like set a motor to 0 volts, you can override that and do that. By default, it just requires that mechanism and does absolutely nothing with it. So if you're issuing like voltage control requests or something in the background with other commands, you will have to probably have your idle command manually re-zero things because otherwise the motor is still going to be doing whatever the last one. Question here?
Yeah, so you mentioned like that for mechanisms, it's mainly to like make it do one thing at a time. So the sequential group for mechanisms will stay the same. Like parallel grouping would be different then, right?
There are still APIs to allow you to make sequential and parallel groups. There are differences there. I also don't have time to talk about that in this talk because we're 18 minutes in and I haven't even gotten to some things I need to talk about. So I think I'm going to pause Q&A in the middle right now so I can get through stuff. There will be time at the end, I hope, for Q&A. I put in the slide for that, so I better reach it. So let's go on from there. So telemetry, this is the second big part of V3. So the V3 scheduler is now protobuf serializable. So you can add this to the new telemetry APIs that's coming up in 2027. You can see this on like any connected dashboard or analysis client that has protobuf support. I'll just briefly talk about most of the things that are in the serialization. So this is because the scheduler knows everything, right? The scheduler knows every command that's running. In V2, the scheduler only knew the topmost command and didn't know anything about what those things were doing under the hood. The V3 scheduler knows everything. So because of that, we can serialize, like, here are all the commands that are running right now, and then the scheduler, because it's scheduling each of these individually, tracks information about those as well. So it knows the name because you have to give every command a name. It knows the requirements of each command because you have to say what each command requires. It also has a unique ID number for every command. So every time a command is scheduled, that particular run of that command gets a new run ID. So if you schedule a command object, it runs until it finishes, that one run gets a unique identification number. The next time that same object runs, it gets a new ID. So you can guarantee, like, if you see an ID number change in the scheduler data, you know that it stopped and started over again. How that happened, that's up to you. That's up to your, figuring out what your program is doing and how that's structured. But you have that information now. It also has a track for the ID number of the parent command that's scheduling. So if you have a composition or a sequential command group or some other larger composition setup, you can rebuild that tree. So you can know what the very topmost command is because that command has no parent ID. And then everything points up. So it's all pointed all the way up. In protobuf, this is all a flat array, but you have your pointers, you can reconstruct that tree. The scheduler also tracks how much CPU time each command takes when it runs. So you can see information about how long it's running. That's not saying how long it's been scheduled for. That's saying how much time has this taken on the CPU. So the hope there is that you can use that information to debug and figure out performance bottlenecks in your code if you're doing like path loading, like JSON deserialization in the middle of your command loops, and you see that, oh, this command is taking like 500 milliseconds last time I ran, what the heck is going on here? You have that information so you can start to debug from that. So here is what what it could look like in Glass. This is the SimGUI right now. This might be a little hard to read for people in the back, but this is showing that full tree, that full list of commands. We've got our drive square command as our parent, that's in slot 0, slot 1, that's our drive distance command. You can see, and that just changed to turn 90 degrees, so this is showing live data. This is showing the last time in milliseconds, the total time in milliseconds, so that's the CPU time that I was talking about. You can also see this in the vendor scope. So this is a concept that I made. This is probably not what it's going to look like, with what you're going to have access to. But you have access to all the data, right? That's all in the protobuf data. So AdvantageScope has access to that protobuf data stream, and we can visualize that. So we can see, our drive mechanism has this big command that is requiring the drive mechanism, and it can also see everything that's inside that drive command. So right now there's only, it's only driving straight or returning, so there's only one entry at a time in here. But if you have a big composition that's doing many things, you'll see multiple boxes in here, essentially, showing the full detailed information about what's running, when it's running. This is on the line graph widget in AdvantageScope. So you can also put in like your triggers, for example, as Boolean data under discrete fields. So you can see when those triggers are firing, you can see that in the line graph at the same time as command, so you can really easily compare, here's the trigger, here's the command that triggered, and you can see when things are happening in the line. We could also see this in Elastic. Again, this is a concept. This isn't necessarily what is going to be finally in Elastic. I still need to talk with people working on Elastic to see what we'll want in that dashboard. Because it's a driver dashboard. We shouldn't really be using it for debugging your robot. But if you're on the field and you want to know at the top level, like, what is my robot doing right now? You have access to that data stream. So you'll be able to see that if you need. So other than protobuf, so there's one issue with the protobuf serialization is that it takes a snapshot of what the schedule looks like at the moment you do that. Usually that's happening like either before or after you run the scheduler. So you don't have access to any of the data, any of the events that are happening inside the schedule. So if you have a one-shot command, as in a command that never yields, so it gets scheduled, it runs, it exits, and it's done. You don't have access to that in the protobuf data because that all happens in a single scheduler loop. So because the proto is a snapshot either before or after that loop, you have no visibility to that. So events are a way of getting access to that. You also have access to more kinds of events than just something running and stopping running. But these are all emitted automatically by the scheduler. You can just add a listener to see, when some event occurs. Every event has a timestamp on it, so that you know when exactly something happened. That's in microseconds on the robot controller time. So that's all timestamp. That's going to be correlated with the timestamps in your data logs. So this is just a subset. So for example, if you want to see what's happening with commands for being scheduled, mounting. So mounting is when a command gets pulled up by the scheduler to run. Yielding, right, that's that yield call for the coroutine. And completed, that's when the command exits on its own. So we have events for all these. You can add a listener, and then that has access to the command that something happened to, as well as the timestamp for that. I'm using var here because this all needs to fit on a single slide, but you could write these types out to be a little bit more easily printable if you want. This is a table. This is all of the current event types that we support right now. So there's that scheduled, mounted, yielded, completed. That's all the basic life cycle events of a command in the scheduler. There's also completed with error. That's basically if you run into a runtime error that gets raised while your command is executed. An event gets issued for that. You can handle it. You can't swallow the exception. The exception will bubble up. That will stop your program unless you're also wrapping the schedule.run call in a try-catch block. But if you're doing that, then you should probably fix your code. So you have access to that. You can log it. You can do whatever you like with it. You have access to the throwable that caused that error, and you can print that out and if you want that, do whatever you want with it, and then it'll make your program crash. You also have canceled and interrupted events. Canceled and interrupted those will both be issued on an interrupt. They'll be canceled first and then interrupted. So if you want to see why things are happening, the interrupted event is pretty handy for that, because that tells you this command was running and was interrupted by this other command that was coming in. So again, you can do whatever you want to log that or print that to console. That's up to you. The idea is that should be flexible, so you have the tools and have access to the data, so you can do what you want. Let's talk about ownership. So this is the last big pillar of commands. So commands require zero more mechanisms. Every running command has exclusive ownership over all of its requirements. Each mechanism, again, can only have one command owning it at a time. If you try to schedule a new command that shares a requirement with one that's already running, it will either interrupt the running command if it's at a same or higher priority level, or not interrupt if it's a lower priority level. Something interesting that we can do with V3 is that because the scheduler knows everything, the nested commands inside your compositions don't need to have the same requirements as the parent. So the earlier drive square command that I showed, that was using a no requirements command, or that could have used a no requirement command, and then run commands internally that require the drive base. And then while those inner commands were running, that outer drive square command would have still owned the drive base. And again, as normal, schedule a new command will cancel all the running commands that share requirements with it. Again, based on the priority list. So for compositions, this is like your sequential commands, your parallel command groups, deadline, race groups, all that stuff. Compositions are basically putting multiple commands together to do some more complicated logic. So you have inner commands inside of outer commands. I tend to call those parents because it makes that relationship between parent, child, grandchild easier to understand. For purposes of interruption, the parent command inherits all the requirements of all of its children. That's recursive. That goes down all the way if you're doing like 5 levels deep of commands. It will inherit everything all the way up. That's all managed by the scheduler. So if you interrupt a child command or a grandchild or great-grandchild command, that will bubble all the way up to the root. So if you have something really nested that's going really low level, and you want to interrupt, you want to do something else with that mechanism, that will bubble up all the way. So you don't have to worry about I have this thing running that's part of this really big composition. If you interrupt that small thing inside while it's running, that will bubble all the way up. So here, this is the no requirements. So this is the parent command itself doesn't have any requirements, right? I'm explicitly saying that. But while the drive base is running, while that's in the middle of that drive distance 10 command, that parent command owns the drive base. So if this parent command is in the middle of driving, and I want to do something else with the drive base, and I schedule a new drive command, that will interrupt this whole thing. And similarly, after the drive is finished, then the elevator command starts. So this will require the elevator command while that single elevator command is running. It no longer requires the drive command at this point. So once the drive is stopped, you can have the default drive command start up. So if that's like set an X, for example, whatever your default drive command is going to be, that default command will be able to run while the elevator is moving. Sometimes you want that, sometimes you don't. If you don't, you can set a default command inside this command. And I'll show how to do that later. So for interruption, I think I've talked about this. I can probably skim this. So basically, interrupt occurs if you schedule a new command that shares at least one requirement with a running command. And then that interrupted command that's already running, that will get interrupted, that will go into the scheduler. You'll see some telemetry events around that. And then this is all skipped if the one that you just scheduled is a lower priority because you have priority levels here. So really basic example here, if you have a command priority 1, you schedule a new command that has priority -1 that shares a requirement, that -1 priority gets ignored because it's lower. So priority levels, those are just integers. So it goes from -2 billion to +2 billion, by default it's 0. So the default idle command that we talked about earlier, that starts at -2 billion integer root value. But you can have finer-grained control. So lifetimes, this is something new in V3. So there's a couple key points to lifetimes here. So one is that an inner command cannot outlive its parent in any circumstance. This applies to commands. So if you create a command inside another one, that inner command will get canceled when the outer one exits. So if you're forking something to run in the background, and then your parent command stops, that fork command will exit. That will be canceled. This also applies to triggers and default commands. So you can make a trigger binding inside a command that will only be active while that command runs. For example, you can probably use this for doing like path following stuff. Like you're following a path and you want to like automatically store when you get to a scoring position. You can have a trigger set up for that inside your path following command to trigger while you're doing path following stuff. And then when that exits, the trigger gets cleaned up. So it cannot, basically, it can't outlive the parent. It can't outlive that scope that was created. Similarly, for default commands, you can create a default command or set a default command inside another command to be the default while that command is executed. And then when that outer command stops, that default command setting gets undone, and the default command reverts back to whatever it was before that command started. Here's the scopes. So there's 3 scopes that are really the only 3 scopes that you have in V3. There's the global scope. This is stuff that's happened like in your robot constructor when your program is booting up. You're guaranteed to be in that global scope during robot class construction. That guarantee does not exist at any other point. So if you want a trigger to always be active, regardless of whatever op mode your robot is running in or whatever commands are currently executing, set up that trigger in your robot constructor or something that's called by that robot constructor. There's also the op mode scope. This is when you have an op mode selected on the driver station. This is new for 2027. Op modes are carrying over from FTC. When you have an op mode selected in the driver station, that op mode is going to be the scope. So if that op mode is selected and active, so your robot is in that mode, that op mode corresponds to like an auto op mode and you're in auto mode, then any triggers or commands that you set up, so if you schedule a command, bind a command to a trigger, you set a default command, that is all limited to that scope of that op mode. So when that op mode exits, all those bindings, all those scheduled commands, that all gets cleaned up, that all gets garbage collected at the end. Similarly, if you're doing trigger bindings, scheduled commands, working commands, setting default commands inside another command, that all gets cleaned up when that outer command is finished. So when it gets canceled, when it exits automatically, however it's over, everything that was set up inside that command gets cleaned up. So that makes it really easy to do triggers internally inside commands. That makes it easy to do default commands inside of other commands. Instead of having to set all that stuff up like externally in your global scope and have to chain like 5 levels of triggers together to make sure that they only fire in a particular mode that you're interested in. So here's an example of that global scope I was talking about. So I've set up a drive mechanism, I've set up a driver controller, pretty basic stuff. But I'm setting a default command and I'm setting a binding to the square button on my PlayStation 5 controller. So this is the global scope, so these will always be active unless overridden by another scope. So my global scope default command is stopping the drive, so the drive just does nothing by default. And the square button, when I press that, will make the robot drive to square. So these bindings are always active. But if I do some other things in an op mode scope, that scope overrides the global. So in my example teleop, my default command for the drive base is now an operator control with my PlayStation 5 controller instead of being stopped. When this op mode exits, that default command gets reverted, and your default command goes back to that drive out stop command. Similarly for this that square button binding, this binding is only active while this op mode is running. So that will override that wherever that binding was in the previous slide, I forget it already. So when I press square, this will now do that drive out status. That existing binding does still exist, but this command will take precedence because it comes later in the binding list. And then lastly, for a command scope, I can set a trigger on, say, like an in shop zone trigger, and then I can await some other command to run. So if I'm like following a path that does like a left side sweep, come back, and you're in your shooter, some predefined zone on the floor where you want to be able to shoot from automatically, you set up a trigger for that. So this trigger will only be active while this smart pathing command is running. When this command finishes executing, that trigger gets cleaned up, it's no longer active. So that really unlocks this kind of really tight scoping, so that you can have triggers only active when you actually care for them to be active. You don't have to bind them like 4 or 5 levels deep, so that you can only have these triggers execute while a certain command is executing. So I've seen a lot of code like that, where you have like tons of global triggers. You don't get any of that anymore. So let's talk about stages of complexity. And this is complexity for your code. So if you're just starting to learn how to use WPILib or just how to program in general, you want to use that imperative API. That's that while loop, if statements, etc. inside that coroutine block. The one thing you do have to know how to use is these lambda functions. You can write class-based commands that implement the command interface if you want to. If you're more comfortable using that kind of OO inheritance, you can use that as well. If you're doing simple sequences, and I really mean simple, like do A, then B, then C, then D, you can use the declarative API. That's doing literally like a command, dot, and then, etc., etc. That's carrying over from V2, so you can continue to use that. But that kind of structure is really difficult to transition if you want to start doing branching logic or anything more complicated. So I don't really recommend using that unless you really have something really simple. If you're doing complex code, again, loops, branches, if statements, switch statements, you can use the imperative API, use async await, forking, etc. That we saw earlier. And then if you want to do something really complicated, there's a state machine API. That's all based on commands, but you can add states that run some command in that state. You can have transitions between one state and the next. So that, if you want to do something really complex, you can use that, still stay inside the command framework. So this is, we saw this already, I'm just putting this up as a reminder. So this is the imperative API. So you're doing your run, you have your function body, you have your while loops. This is all basic Java stuff. And this is the intent, is that you can use basic Java code that you already know how to use and really easily transition to command suite 3 coroutines. Again, the only thing that you really need to do to change your logic is adding that coroutine.yield. Everything else is just wrapping that existing function with the requirements and the name. And again, actually just a side note, if you don't have that return call, if you just do that run without actually using that command object, that's compiler error. So you can't forget to use your commands now. Declarative API, again, I'm not going to even bother doing that drive distance command using the declarative API because it's awful. Just don't do that. But again, if you're doing simple sequences or parallel groups, this is a pretty easy DSL to use if you're familiar with that, and if you don't want to go to the whole, coroutine await bunch of times. And then state machines. This is a little more complicated, so the font's a little bit smaller because you have to do a lot more. So it's not very well suited for doing simple things, but it's pretty good for doing complicated stuff. Particularly if you want to be able to go from one state to a previous state pretty easily. You can set up transitions for that. That's still a little bit work in progress. That's not yet been merged into WPILib, but it'll probably be going in fairly soon. And there will be examples and documentation for all of this as well. So let's do some one-to-one comparison with V2. So in V2, right, you've got your init, execute, is finished end functions. You're doing class-based commands. That corresponds to run first, finally do, execute, etc. With the DSL. V2 also has a lot of things as escape hatches to get around limitations of V2 and the scheduler. Deferred command lets you instantiate a command at runtime instead of upfront when you're creating your command compositions. That's useful if you want to do something dynamic on the fly. Proxy command makes a command that doesn't require anything for a composition so that you can have default commands running in the background when the thing that you're proxying is done. Select command is basically a switch statement. You have a bunch of predefined states. You have a map of those states, and you say what command to run when some state is reached at runtime. Conditional command, same thing, except it's just true, false, like an if statement. Wait command, it's just saying wait a big amount of time. That's all gone. You don't need any of that stuff anymore. So for the lifecycle methods, init, execute, etc., this is what normally it would look like using the DSL that we've got right now. This is only needed because V2 has no way to yield, right? So you have to split up your logic. So you have execute is basically your loop function, and then everything else like your loop condition, some exit code to run when the loop is done, some init code to run before the loop is entered. So you have to split all of that up because V2 needs that because you have to split up your own code so that it can run in slices. In V3, with coroutines, you don't need to do that. You just write a while loop, right? And then because it's just normal Java, you can also have if statements, switch statements. You can do whatever you like in here without needing any of the commands, DSL or framework stuff on top of it. So deferred command also gone because V2 is declared ahead of time and doesn't have that kind of dynamic runtime stuff that you can do inside your execute methods of commands. You have to have deferred commands so you can have that kind of dynamic behavior at runtime. V3 can be dynamic, that's the whole point. You have the whole function that runs at runtime. So in V3, creating an inner child command is like a deferred command. It's the same thing, it's the same concept. So here for that smart pattern command I showed earlier as an example, that follow path, that's getting instantiated at runtime. So this is the first, this is dynamic. If you don't want that, for example, if loading a path takes a while, if you're loading a ton of JSON and deserializing it, you can predefine that if you want. Because it's all just objects under the hood at the end of the day. You can just predefine that follow path command so that it's, you load your JSON, you deserialize it, that's all done ahead of time so that you're not paying that time, you're not paying that performance penalty at runtime. So that's just converted. You just declare it ahead of time and then you just wait for that object layer. It's pretty easy to reuse command objects because the scheduler is smarter. You don't have that, what was that error? Like this command is already in composition, you get a runtime crash because you're trying to do that. You don't have that. Proxy command. This is a huge pain in the butt for everyone. This is because the V2 scheduler only knows the topmost stuff. So your command compositions, like you're making a sequential command group, inherits all of the requirements of every command inside of that group. There are some V3 corresponding APIs that do the same thing, if that's what you want. And sometimes that is what you want. But by and large, most of the time, that's not really necessary, especially if you're providing custom default commands inside your compositions. So this is only necessary because the subsystem, or the V2 subsystem needed that requirement. This is a way of doing the escape hatch. So in V3, because the V3 scheduler knows everything, if you interrupt a child command that has some requirement, that follows up all the way. So that's fixing the problem that proxy commands were kind of papering over V2. And again, the child commands act like proxies by default because this parent command has no requirements, right? So it inherits the requirements of any inner command while that inner command is executed. So if you have this shoot on the move command, bind to a trigger, this will require the shooter command while that shoot on the move command is executed. But the rest of the time, it doesn't need the shooter. So your shooter default command can execute. If, for example, you want to lower your hood by default so you don't hit yourself going under the trench, that default command is able to run while this composition is executed. Select command, condition command, also not necessary. Use an if statement. That's all you need to do. Wait command, kind of similar. Because V2 is built on commands and has the primitives, you have to use commands for everything. So you have to write a new wait command, or you do commands.wait for whatever API you feel is using. But because V3, you have access to this underlying coroutine. That underlying coroutine is the primitive. So you just call coroutine.wait. There you go. If you want to drive for 2 seconds, that's all you need to do. You just set your motor, you wait for 2 seconds, and then just set your motor to 0. That's it. So yeah, out of time, I think I timed this pretty well. I put the slides deliberately. So here's a bunch of things that I knew I wouldn't have time to talk about, and I'm probably not going to have time to talk about. So there's trigger latching. So in V3, if you have a trigger that's listening to some Boolean event, that trigger value will stay the same for the entire loop cycle. In V2, that doesn't happen. So a really degenerate example is you have a trigger listening to a random number. That random number gets reevaluated every time the trigger gets evaluated. So if you're logging that trigger value that actually makes a command run or stop running isn't going to match what you have in telemetry, which is awful. So in V3, that's latch. So that value stays constant over the course of the loop cycle. Rise and fall edge triggers. You can probably figure out what those mean. I don't think I need to spend even more seconds on that because I got 40 left. Compile time safety. I touched on this earlier. There's a lot of compile time checks built into WPILib now. We have a custom Java compiler plugin that does all of this. This checks like if you're creating a command element, you actually use it. You bind it to a trigger, or you fork it, or you schedule it, or you do something with it. You can't just create a command and do nothing with it. Similarly, command stack traces, because it's all asynchronous, our command stack traces also show where you found that command, where that command started to run. So you don't just have the stack trace of what is happening inside the command, you also know what happened to make that command get scheduled in the first place. So you can go back and say, oh, this trigger was where this was bound, so I can just go back and find out. Nested mechanisms is like a swerve module can be a mechanism inside like a larger swerve drive-based mechanism. Those swerve modules can be private and internal, so nothing externally has access to them. And because the compositions are smart, like they can all be private, you can have commands that use those inner mechanisms that are all kind of required by the algorithm. And under the hood, I really hope there's no Oracle employees here because you're going to hate me for this. We're using continuations and internal JDK classes to do all of this. Java 21 introduced virtual threads. That's the basis for being able to have suspendable functions in the first place. It's all internal APIs. We're getting access to that. Again, Oracle will hate me for doing that, so I'm not going to hang myself on that. And there may be time for Q&A. Question?
Why is there a dedicated coroutine output rather than just an earlier to the function?
Why is there? I didn't catch the end.
If you want to exit out of coroutine early, why do you have to do coroutine output instead of just returning?
So coroutine.park is basically an infinite loop that just yields forever. So that's basically, so you would use that if, for example, you're doing something off-board on a motor controller. So you issue like a voltage request or a PDA request or something, and then you let the Talon or the Spark or whatever do something on its own. But you still want the command to be executing, because that command is what you're going to see in telemetry. You're not going to see what the motor controller is in telemetry. So for example, you would say, I want to set, say like a PID command to a motor controller. Say, I want to spin a flywheel to some RPM, right? And then you park that coroutine, and then you let the motor controller do its thing asynchronously. But in telemetry, you're still going to see that spin flywheel command in telemetry while that's running, and then you can interrupt that later with another command. So that's why that exists. Any more questions here?
Will there also be support for C++ and Python for all of that?
Good question. Right now, this is only for Java. So that's because like the underlying frameworks that we use is very language specific. The second part is that Java is currently about 90% of teams. So this is going to have the most reach as a Java only framework for now. We do want to make this for C++ and Python. That's going to look very different potentially. C++ doesn't really have compilers in the right spot to use C++ coroutines right now. Python does have coroutines built in. We still need to do some research to see if we can do the kind of deterministic control of those coroutines, because we need to say like this command is always running before this other command, right? So we need to guarantee like that parent-child relationship, as well as we need these robot programs to be deterministic, right? Because you need to be able to reproduce behavior, you need to have sensible telemetry. So we got to circle out. All right, so that's the end.